right, we're now broadcasting. I can see the attendees are joining us here. We'll give them just a minute, let everybody get in the room with us. All right, good morning, everybody. Thank you for taking the time out of your day and joining us this morning. Got a good webinar put together on rod load and reversal, kind of going through what's your data telling you. You're collecting that data from a compressor, and how are we going to relate that to the compressor internal components. As you can see, I've got Mike and Brian here with me again. Kind of want to give them a shout out, say thanks for doing these webinars. I know we've gotten good feedback from them. Lots of customers appreciate you guys, doing these webinars for us. There's a new thing going out there called Zoom bombing, unfortunately. With these Zoom sessions, I guess people are trying to hack in and take control of the session. If that were to happen today, just go ahead and log off, leave the session, and I will end the session from the back end and we'll get it rescheduled as soon as possible. You want to go to the next slide there, Mike? So as I said, I'm Dylan Abel. I've been with the company for coming up on eight years now. Worked through some various roles as online systems engineer, technical services manager, and most recently I'm our product manager. Work with new product development, taking an idea just across the company to get a product launched into the market, and then lead our product life cycles. And I believe next here is Mike's intro.
Hey guys, yep, this is Mike Jones. I've been with Windrock for about 15 years and about 50 years in the industry. And I've tested just about every piece of equipment that you can think of out there that reciprocates. So we'll let Brian go next.
Hey, good morning, everyone. Thanks for joining us. I've been with the Nalco for about 17, 18 years. But I've been doing this for about 40 years now. Got a little bit of engine, compressor, diesel, you name it. So glad to be with you guys.
Awesome. Thanks, Mike and Brian. First, just kind of want to hit on who's Apergy, who is Windrock, and a little bit of our products, and we'll jump into the material for today. So who is Apergy? We're formerly Dover Energy. We're now Apergy, comprised of about 15, 16 companies here. You can see we've got Theta, Oil Lift, US Synthetic, Kortstein, Norcell Wellmark, various technologies from drilling technologies, artificial lift, automation technologies is where Windrock comes into play with our remote monitoring and IoT systems, and then production equipment. I think next we'll dig into Windrock. Who is Windrock? Windrock's been around for over 20 years now. Started by a few employees that were bought the technology out from CSI, which is now part of Emerson. Bought out this technology, created Windrock, and helped grow it to what it is today. We've had four generations of portable analyzers, starting with the 6300, and most recently we launched the 6400. Got various online systems. We had OnGuard, which is kind of the first generation online system, and now we have Platinum. These are your real-time monitoring systems, and we have Auto Balance, which is an add-on to Platinum, and it's helped to balance a slow-speed integral engine and keep it in equilibrium. Our newest product is Spotlight. We've got various versions of it. We've got Spotlight for compressors, and then Spotlight for high-speed engines. So jump into each of these a little more. First up here, you see Platinum. Platinum's really that permanently installed, permanently mounted online system with real-time data. It's collecting data and doing the calculations as fast as it can, serving that data up to a computer for real-time analytics. As I mentioned, Auto Balance is kind of an add-on for those slow-speed machines. Next, we have the portable analyzer. This is really Windrock's kind of first product, what it's most well known for. Portable analyzer, an analyst takes this analyzer out to a compressor engine, hooks up pressure sensors, accelerometers, ultrasonic sensors, collects this data into the analyzer, and then takes it back to their desk, their control room, transfers that data over to a laptop, and then does their analysis on that machine. The analyzer most recently can now send its data up to the cloud into our enterprise software, where then you can view your entire fleet and have some more in-depth analytics. Next, we have Spotlight. As I mentioned, we've got Spotlight for compressors, where we're taking head end and crank end pressures, suction temperature, and a crosshead vibration point. We do use theoretical discharge temperature for the calculations. Spotlight's really a low-cost, easy-to-install solution. IoT, so the data's going to the cloud. It's really meant to monitor, hundreds of machines at once. You install it on 100 machines, and it really helps what machine needs some more in-depth analysis. It'll raise its hand and let you know, unit 2, you need to go out there with the portable analyzer and take some more data. And then we have Winrock Enterprise, our newest software. This is used both with the portable analyzer now as well as Spotlight. We are working on Platinum connecting to Enterprise as well. Enterprise is our high-level dashboard. You can view your entire fleet, or you can drill down into one machine. It's got some AI built in for leaks. We've now been able to detect leaks, 14 days in advance. Suction, whenever I say leaks, suction discharge valve leaks. So it's really a high-level dashboard that allows you to drill into one machine. Go to the next one there, Mike. So where our systems used, kind of worked with our customers, got an outlook of the market on how do we divide up our machines, our products with respect to the machines. So there's about 20% of the machines out there that are your critical assets. These are crucial to the process. They require a shutdown because at the sign of an issue, because you don't want to have a catastrophic failure. And this is where Platinum comes into play with the real-time data updating almost every second. It's got built-in relays, so you can send a signal to, say, your PLC to shut down the machine before there's a catastrophic failure. And you've got 75% of the assets out there that are essential. So this is where you install Spotlight across your fleet. It'll raise its hand and let you know where you need to go out with the portable analyzer to take data that day. So I think this is my last slide. At this point, I'll hand it off to Mike and Brian, and they'll start into today's material. Thank you.
Okay, guys. This presentation is going to be in 2 parts. I'm going to talk about the rod load, and Mike will talk about the actual pin load. So if we look at this cutaway view of a compressor, you notice that the piston's in the cylinder to the right there, and the rod is attached to it. So the gas forces here inside the cylinder will act on the rod, and then the forces will also go through the rod into the crosshead, and it'll start acting on the pin and bushing there. So the software actually measures 2 points here. It's going to measure the rod load, and it's also going to actually measure the pin load for you. So Mike's going to talk about the pin part, compressor pin part later. I'll talk about just basically the rod loading right now. So I guess you can ask yourself a question: what's the weakest link in the crosshead? If we go back to that last slide real quick, Mike, if you look at all these components in this compressor here, I mean, what is the weakest link? If operations puts too much gas pressure in the cylinder, will the piston break, or will the rod break? Or if it overloads that cylinder, will it wear out the bushing, in the crosshead? Or will it break at the actual threads, where we screw it into the crosshead? So every manufacturer has a different location for its weakest link. And it's really important that you know your equipment, so you can set up the software accurately and tell what's your rod load, all right? So we're gonna talk a little bit about that more later. The next slide here shows us just a basic pin, a piston and rod here. So that's what I'm gonna talk about here. This is called rod load. Okay, so basically it's the gas force on each side of the piston face. So when the piston's moving forward, right, the pressure on the head end is greater than the crank end. So it's actually bending the rod. And then when the piston's moving from top dead center to bottom dead center, the pressure is greater on the crank end part of the piston face. So the rod is actually stretching. So within one revolution, the rod bends and stretches. So this is rod load. It's kind of like a coat hanger effect. You know, it can bend and stretch for a long time, just like a coat hanger. You can bend a coat hanger and you'll never break it. But if you bend it too much, it'll actually snap, right? So manufacturers know how much this rod can bend and stretch, and they give us a limit. So the software will calculate the rod load, the actual rod load, and compare it to the limit of the manufacturer. Okay, so the next slide shows pretty much the formula for gas force. And it's a real simple formula. You can do this on a calculator, actually. So the gas force on a crank end is actually equal to the pressure on the crank end times the area of the crank end. And that's it. So if you look at the formula at the top, gas force CE, so the top there, Mike, for me? There you go. So to figure out the force on the crank end, all we have to do is take the crank end pressure, PCE, times the area of the crank end. So the pressure is real easy to get, and if we know the bore and the rod diameter, we can calculate the area very easily also with these formulas right here. So that's the force on the crank end. And then the bottom one here is gas force head end. So once we calculate the force on the crank end, then we have to calculate the force on the head end. So the software is going to do two formulas here. It's going to do the gas force on the crank end, then it's going to calculate the gas force on the head end. Once it does these two, it has to subtract the two, and that's your actual rod load. And that's gas force only. This has nothing to do with the weights or the inertial forces. Okay, we'll go to the next slide. Here we're talking about the compression calculation. So to figure out compression calculation, we're going to take the head end pressure, okay, and we're going to actually the area of the head times the discharge pressure. So when the piston's moving from bottom to top dead center, the pressure is greater on the head end. So that's why we're going to use the head end discharge pressure. And then you're bending the rod. You can see the rod here is kind of bending on us, right? But we do have a little help from the crank end, right? So we have to get the force on the crank end. So that's when we're going to take the suction pressure times the area of the crank end. So once we figure out the force on the head end of the piston and on the crank end of the piston, we're going to subtract the two, and that's going to be our compression calculation. And this is going to be expressed in pounds force, because basically it is force, right? And the higher the pressure, the more force we have. So that's the calculation for compression. Next slide shows us the calculation for tension. So tension calculation, like I said, this is when the piston's moving from top dead center to bottom dead center. So now when the crosshead is pulling the rod back, we have more force on the crank end, and we have a little bit force on the head because the crank end now is in compression and discharging. We have more force on the crank end, and it's actually stretching the rod. So you can see here that the rod is being stretched in the picture. So the calculation for tension is basically the same thing, but now we're going to take the suction pressure on the head end times the area of the head end, and then we're going to take the discharge pressure on the crank end times the area of the crank end. And we're going to subtract the two, and that's going to be our tension calculation. And this is also expressed in pounds force. And it's that simple. So this has nothing to do with weights. This is all the pressure inside the cylinder on each side of the piston face. All right. Next slide here shows us a drawing of the actual gas force here. So the green line here is the gas force in one revolution. And then you can see here the maximum tension, the red dotted line is 30,000 pounds force at the top there. And then the maximum compression is more, it's actually 32,000. So basically for rod load, we're gonna look at the green plot. We don't want that green plot to touch the 30,000 or the 32. If we do, we might be overloading the rod. So this picture here is the rod load plot shown in the top half. So to get a rod load plot, we definitely need a head end and crank end pressure. If you don't have a head end pressure and you have a crank end pressure, the software will not calculate your rod load. So we always have to have a head end and crank end pressure in order to calculate. So if we go to the next slide here, if you don't like to look at it that way, you can look at that gas force in the middle of the plot, right? So all we have to do is right key click on the plot, go to options, and right here to the right, you're gonna see rod load plots, and we'll grab overlay on main. So if you do that, if you go to options and grab it on main, we'll go to the next slide. We can see now that the gas load here now is overlaid on top of our head end and crank end. So some people like to look at it this way. It's a little easier to look at, and we can compare the data. Okay, so basically what the software does here, it calculates the gas force at every crank angle degree. So if you remember those formulas we was just looking at, the next slide here is a zoomed in view of what the software is actually looking at. So the software looks at it per dot. We look at it in a line trace. So if you go to degree number 1, right, degree number 1 shows us that the suction pressure, and that's your gas rod load right after degree number 1. So if you look at your gas pressure for the crank end here, it's at suction, it's around what, 140. Okay, so that's our suction pressure on one side, the piston face. And if you go to the head end discharge at degree number 1, yep, it's about 315. So the software is going to use the 315 and the 140 for the pressures, and it's going to calculate the rod load. And then it's going to come up with about a rod load of degree number 1, Mike. The rod load here, degree number 1 is about 45,000 pounds. So if you look to the left, all the way to the left, you're going to see your rod load plot there. So it's somewhere between 25 and 50, probably around 40, 45,000 pounds force. And then as the piston moves another degree, now the software is going to sample the pressure data at degree number 2. And now it's going to use the pressure data at degree number 2 to calculate the rod load, the gas force there. And it's going to do the same thing for degree number 3. So the software is actually going to calculate 360 rod load plots for us in one revolution. If you go around 45 degrees there, Mr. Mike, you can see that the heading and crank end pressure is pretty much equal, right? So if you think about it, if the head end and crank end pressure is equal, then our rod load should be 0 because the forces on each side of the rod is equal. So, and you can see here that the software plotted it right at 0. So this 0 line here, the red dotted line is our 0 rod load. So far from 0 to 45, the rod load's been in compression. And now you can see the green line goes from compression and now it goes to the top of the dotted line. Now we're in tension. So now there's more force on the crank end, which is the blue dotted line there, and less force on the head end. So now the crosshead is actually pulling the rod back because it has more force on the crank end. So we went into tension and now it does the same thing. So now we continue into tension and then eventually we're going to go back into compression. So our rod will go into compression and tension, back into compression every revolution. Okay. So our next plot here is the actual software looking at the plot for us. And you notice cylinder number 1 here, the absolute load pounds force is 20,413. So the compression on this particular cylinder is 20,413. And then if you look at the tension, it's 18,313. And the next column is telling us percent load. So it's telling us that that rod is 63.8% of compression. And then it's going to divide the actual 20,000 by the 32,000 where Mike's pointing at right now. So this software calculated 20,400 and it divided it by the 32,000, and it said that that rod load is only 63% load. So the objective here is we have to make sure that in the software, we have the correct manufacturer's limits here. So in this particular unit, we did go to the manufacturer. They did tell us it was 32 for compression and 30,000 for tension. So sometimes this is a hard number to find. Sometimes it's on the actual tag of the compressor. Sometimes you have to look in the book. Sometimes you have to make a phone call. But we need to get this information correct. Because if I would have said this rod load is 100,000 manufacturer specs, but then my percent would only be like 10%, 20%. So I'm really undershooting it and I can get in trouble that way. So yeah, we have to make sure that the rod load limits are correct. And if you notice down here in the notes also, this is from an Ajax compressor, okay? So Ajax rates their rods a certain way. And Dresser rates their rods differently, and Ariel rates their rods differently. So everybody has a different way of rating their rod. So some guys, they rate the rod itself. Some guys say that the weakest link in the throw is the bushing. So you have to make sure that you know your equipment and you check the right manufacturer and you get the right rod load limits. Okay, so the software helps us here. So if you go to setup software options, and then in the software options window, you go down here to the rod load and reversal. And you're going to see here at the top, what we're talking about here is rod load calculation method. So later on, Mike's going to talk about the actual pin load. Here, we're just talking about rod load. Remember, there's two different components here we're going to look at. The software is going to look at the rod load and then the pin load. So at the top portion of this window here, rod load calculation method, I'm checking OEM. And then I'm going to hit my drop down window there, and I'm going to grab the manufacturer of my compressor, whether it be Ajax, Ariel. So there's a list here that we can look at. And then when you check Ajax here, you notice that the rod load calculations detail tells us Ajax uses the suction and discharge toe pressures to calculate their gas force on their rod. Says that it does not use the inertial forces. So in the software here, there's 20,413 down here on our rod load report here. Cylinder number 1, stage number 2 is 20,413. That's because the software is going to look at the suction and discharge toe pressures, and it's not going to use the weights. It's just using the toe pressures to calculate that 20,413. And the same thing with the tension, the 18,313, it's using the toe pressures. So if I was an engineer or a mechanic, I can just go up to the gauge readings on the panel because the gauge readings should equal the toe pressures. And I can just take out my calculator, use my gauge readings for my rod load with the area, and I can calculate this 20,413 very easy. So Ajax is really making it very easy for us. It's just using the toe pressures. So the next slide is showing us here that this is a Dresser-Ran compressor. So you notice here, the OEM, I checked Dresser-Ran. So when I check Dresser-Ran here, you notice the gas forces are different. It's not using the toe pressures here. So Dresser-Ran is telling us for our rod load, we're going to use the max differential pressure degree by degree. So that is the total pressure that the piston face sees. In other words, it's not using the toe pressure, it's using the actual highest pressure in the cylinder, which is basically without valve loss. And also you notice that the inertial forces here, Dresser-Ran says, hey, you need to use your max pressure per degree in the cylinder, and you need to use the weights of the piston, the rod, and the crosshead mount. So if you think about this, the gas forces plus the weights, that's what's acting upon my crosshead pin and bushing. So what Dresser-Ran saying is here, we don't really rate the rod. because you need to use the weights and the gas forces together, that's the forces at my pin and bushing. So Dresser-Rand actually rates the bushing, the crosshead bushing. They're saying that that's the weakest link in my throat. It's my crosshead bushing. So if you overload the cylinder, the crosshead bushing will start wearing. The rod should never break in this particular unit. And then if you look down at the actual the report here now, for the Ajax compressor, it was 20,413 compression. Now you see the report here when I check the Dresser-Rand, it's higher than the 20,413. It's actually 2,000 pounds higher. That's because we're using a higher pressure and we're using also the weights. So see how it's important to make sure that you have the right information checked here in your software options. All right, so that's the Dresser-Rand model. The next slide shows us the aerial model. So if you check the aerial model, here the Winrock software knows now that the rod load calculation details, the gas forces is using the average suction and discharge event pressures. So remember, Ajax used the toe pressures, Dresser-Rand used the maximum pressures. Well, aerial does something different here. It says when that suction valve opens to the time it closes, I want to take the average pressure there. So however long, how many degrees it was open, take the average pressure. And it does the same thing for the discharge. It goes to the discharge side and it knows where the discharge valve opened and where the discharge valve closed. And it's going to look at all those pressure samples in that little area and it's going to get the average pressure. And then it's going to calculate the gas load without inertial forces. You notice here that Aero says we don't use inertial forces when we rate our rods. So what they're saying is that our rod is the weakest link. If you overload the compressor cylinder with pressure, you actually break the rod before you wear out the crosshead pin or bushing. And if you notice here now, the 22,319 is just a little bit different than the Ajax and the actual Dresser-Rand readings. Okay, so in order to get a, if you overloading a rod, if you're overloading your rod now, the only way to decrease your rod load is to decrease your compression ratio. Because remember, it looks at the head-end pressure and it looks at the crank-end pressure. So it looks at the suction and it looks at the discharge. So the wider the suction and discharge pressures are, the higher the rod load will be. The smaller the compression ratio, the smaller your rod load will be. So that's why, like at pipeline stations, you really don't have high rod loads because you have real low compression ratios, right? So when your compression ratios start getting up there, that's when you start having rod load problems. Also with big pistons, if you have a real large piston size, you can get into rod load issues. But the main thing is compression ratio, decrease it, that would decrease your rod load, okay? So that's a little bit about rod loading. The next slide here is just an example of a deactivated head end. If you notice the actual blue trace here is a flat line, that's our head end pressure and it's deactivated. So we have a suction valve deactivated it and it's just staying at suction pressure. But we do have a crank end pressure and it is compressing on the crank end. And we do get a rod load. So we want to make sure that this rod load goes into compression and tension. And Mike's going to talk a little bit more about that. But what I'm trying to point out here is I've seen some analysts say, well, my head end's deactivated, it's not pumping gas, I'm not going to take pressure on it. But no matter what, you want to take pressure on the head end and crank end always. And this way the software can calculate rod load and pin load for you. So no matter if it's deactivated or loaded, you always want to take pressures on both ends of your cylinder. So that's a little bit about rod loading. I think Mike's going to take over here a little bit, talk about the pin load.
Hey, Brian, you want to answer these couple of questions real quick that
Absolutely.
came in while
Yes,
you were
sir.
speaking?
Yeah, sure.
So the first one is, it's from Ralph. When it calculates the rod load, does it use absolutes or does it matter?
It uses absolute, yeah.
The next one here from looks like Javad Esmil. If the OEM doesn't specify the rod load, how do you specify it?
Yeah, that's a hard one. I mean, we do have our Winrock geometry table. You can look up your compressor in there. And if you want to trust that data, what I do is I try to find, like I said, Ingersoll Rand HHE compressor in our geometry, Winrock geometry table. You might have about 10 to 15 different HHE compressors. And if you see your rod diameter in there, I'll look at several different ones and I'll try to maybe get an average of those. Mike, you got any other way of looking, of trying to figure out rod load if you don't have it?
Yeah, at least Ariel makes it easy on us. You know, if you've got your sizing program, they give you all that information. But
And it's on the tag too. Yeah, you can find that on the tag for Ariel. Yeah.
Right. Some of the Dresser and Worthington, some of those others, especially the older ones, are real hard to find that information.
Yeah.
And another thing, you have to make sure that you're getting the information for the rods you've got in there. We have some aftermarket rods and we have the OEM rods, and their tension might be different.
That's a good point. The material is different. That's right. But yeah, I mean, the best way to do is, I believe we have that in our website. And I think it's also in the help section of the MD software.
Yeah.
And it's called the Winrock Geometry Program. And if you can find some of your equipment in there, you can match it up. Yes.
And another one here for a revamp project. Should we calculate rod load at the safety valve pressure?
I've never heard of that before. The safety valve pressure is your relief. So when that pressure gets to a certain point, it will relieve the pressure. So all you're looking for at your safety valve pressure is the actual pressure at that valve. In other words, if you go over that pressure and it starts relieving, it's not really affecting the rod load as much as your vessels. So a safety relief valve is more for your suction bottle or your piping. You know, that's the max allowable working pressure in that vessel. And that's what it's relieving. So the internal cylinder pressures is really affecting the rods. That's what we're trying to look for.
The last question here is, what happens when you have tandem cylinders?
Yeah, that's a good question. We've been working with that. That's a very hard one. We can get the actual head end, the outboard rod load, but the inboard rod load is not quite, and the software hasn't handled that quite yet. So we're working on that. You know, it's just hard.
Well, I've seen a lot of tandems where the crank end was more or less just unloaded and an atmospheric. So there had been times where I'd actually just pull the pressure transducer off and take an atmospheric pressure for the end that's is in that condition, and then I could get some quasi rod load calculations doing that.
Yeah, but the problem with the inboard, like Mike's saying, the problem with the inboard rod is it sees the pressure and the force from two separate cylinders.
Yeah.
Mm-hmm.
So in the software, we have to say this is cylinder 1 and this is cylinder 2. You have to separate the cylinders.
Got it.
Yeah. So it's going to calculate the rod load for the outboard cylinder and the inboard. So the inboard cylinder though is actually seeing two different cylinders on together. So
I think that's all the questions right now. We'll get to some more here at the end.
Okay, thanks, Dylan. Thank you, Brian. You taught me stuff I didn't know.
okay.
I enjoyed that. Now we're going to talk about the crosshead pin load, and mainly what we're talking about, that crosshead pin has to swap directions a couple of times every revolution in order for it to lubricate. And what we're going to be talking about is the crosshead pin and bushing is comprised of two different forces we've got in there. We've got the inertia, which is the mass and speed, and the static, which is the gas load forces. And like I said, we have to reverse that the loads on that crosshead pin and bushing every revolution so that we could lubricate it. And this is kind of another one of those plots where we can actually see the inertia load here. Now this is the pounds of force that's being generated by the instantaneous acceleration of the masses of the crosshead, which all the weights that we have entered into the software. And this works exactly the same way as what Brian was talking about. We're taking this instantaneous acceleration per degree and calculating it at 1 degree increments. Okay, then we have the gas load down here, which Brian talked about, and it's showing its normal track. Okay, now the red marker, that is red, isn't it, Brian?
The total is red.
I'm colorblind.
Yeah, that's the total there, Mr. Mike.
Anyway, so we can see the total here is kind of an algebraic sum difference between these two here. So we've got an inertia load is actually in the higher speed units really dampens the gas load by quite a bit, and in the slower speed units it's just the opposite. The gas load actually, I mean the inertia load dampens the gas load, and in the high speed units it's just the opposite. The gas load actually dampens the inertia load. So when we're getting up 12, 1400 RPM, this inertia load can go quite high. Another thing about that is that, you know, we always, on gas forces, we always cross zero right at pressure reversal, right here. So it always crosses zero on the gas load right at pressure reversal. Well, that's not necessarily true with the total load, because the way these two forces interact with each other, our pressure reversal or our dynamic reversal might be this point and at this point. We can tell by looking at this is a fairly high speed unit. Okay, and what we're talking about is the inertia load is the force in the cylinder that's resulted from the change in their velocity. Okay, as the piston takes off, we create quite a bit of inertia because we have quite a bit of acceleration going on then. Then when the piston starts to slow down, then we have just the opposite effect. We have deceleration, which also creates a force in there. And another thing that we need to remember, if we had both cylinder ends unloaded, the inertia forces are always reversing on every revolution of the crankshaft. So they're always going to go positive and negative, no matter what. And then this is the the reciprocating inertia forces are caused by these masses here. Okay, so we have the piston mass, we have the rod mass, we have the crosshead mass that also includes jam nut, balance weights, whatever we happen to have attached to that crosshead assembly. Okay, now we have a connecting rod here, but we don't include that on any of our inertia calculations because it's a pretty complicated thing, that which part of this is rotational, which part of it is reciprocating, and it's different for every manufacturer. So they don't really include that. No manufacturer includes the connecting rod weight in any of their inertia calculations. Okay, so as these go back and forth, that inertia from that actual weight slings back and forth, and it causes a force on the same components that you're causing force on with the gas load. Okay, here's kind of a little chart here where we can actually see the displacement of the piston as it goes from top dead center to bottom dead center, back to top dead center. And we can see it kind of flattens out a little bit on both ends and also in the middle. That's because we have several degrees of crankshaft rotation at both top dead center and bottom dead center where we don't have any piston motion at all. So that slows it down right in that area. Okay, now the velocity here, now we can see the piston as we start out at top dead center, we're going to be increasing in speed because of the ratio between the connecting rod and the crankshaft webbing. So we're going to speed up right here to where we get to just before 90 degrees, we have maximum piston velocity here. Okay, as we go all the way back down to bottom dead center, then we have no velocity at all at 0, 180. Then as we start going the other direction, we just past 270 degrees, we have another point where we have maximum piston velocity. Okay, when we hit piston velocity though, our highest piston velocity, we really don't have any inertia going on there at all. Okay, and we see here that same thing here where we go our tension load and our compression load by inertia. And it shows here with no gas load on it at all, we have 157 degrees of reversal and tension. We have 197 degrees of reversal and compression. So it's always reversing. Okay, your net load is, or your total load is just simply the sum of the internal and the gas, the inertia and the gas forces. It's calculated for each degree of crankshaft rotation, and the reversal occurs after the net rod load passes through 0 pounds and has met the manufacturer's requirements for reversal. And just like a rod load, like Brian was talking about, most manufacturers have a specific criteria of how many pounds of force you have to have above 0, how many degrees of force you have to have above or below 0 to actually qualify to be a reversal. So that's another thing that you need to find out from your manufacturer. Okay, your rod reversal occurs when the combine of the pressure and inertia forces, actually reverse that pin in the bushing, and it's also called load reversal. Now we hear that called rod reversal. Say we got rod load, we got rod reversal. Well, that's just kind of a generic term that we've got going on for that, but actually what we're looking at is the pin reversal. That's what we're wanting to go with. Now these are just some examples here. See, we have our head end, our crank in pressure traces here. We have the resulting rod load plot here that shows the inertia. It shows the gas load, shows the total load going on in there. And this is from your setup in your geometry that shows where the weights are. Okay, we have the piston and rod mass in this column. We have the crosshead mass in this column. Okay, now the thing we need to remember is that when we are putting these weights in here, depends on what the manufacturer wants you to put in there. If like Ariel, they're concerned with rod load, so we'd need the piston and rod mass in here. Okay. If we had, like Brian showed us the dresser ran, they're concerned with pin load, so we would put all of these weights in this column here to get your total loads. Okay, now when we're looking at reversals, it uses both of these columns. Okay, so it'll use the inertia in both of those columns to calculate your reversal. As we can see by this chart or this report here, that we're showing our reversals here. This is showing the rod reversal in degrees in compression and tension. Like this cylinder number 1, we have 67 degrees of compression. We have 202 degrees of reversal and tension. And then it shows that the rod load limits are 40,000 pound compression, 37,000 tension. And if we see the rod load calculation method is OEM Ariel. Okay, so we wouldn't expect these rod loads to change no matter what we do with the weights in there, because they just don't, because Ariel doesn't use them for the rod load. But you have to have both components in there in order to calculate your reversal. Okay, if we go here and we move all the weights over into this column, then we should see something change, shouldn't we? It certainly changed where the lines cross. So we can see our total loads go here with these weights in this number 1 column, because this total load here is dependent on what your inertia calculation is. So we have a dynamic reversal occurring here, and we have one occurring here. Okay, if we put all of our weights over in this column, we can see that our dynamic reversals now, because we have increased what the inertia calculation is, we can see that this dynamic reversals here are now here and almost all the way to bottom dead center over here. I can't see that Dylan's in the way. Okay, so if we you know, delve in that a little bit more. Oh, by the way, this is our new software coming up, 5.1. You'll be able to have a pull down box here, so you can change your weights in here and actually watch your data change on your plots as you do it. Okay. So now we change that and we see absolutely no difference in the rod load, because why? It's because Ariel doesn't use the weights to calculate rod load. They're using the average suction, average discharge amount, like Brian says, the average pressure from when the valve opens and the valve closes. Okay, and it changed the rod reversal none either, because it's using both of the columns. Either way you look at it, it's using both of the columns to calculate your reversal. So those things have stayed the same. Okay, if we look at it again, let me see. Yeah, if we look at it again, and we just put the piston and rod mass in here. Okay, then we go back to the original lines of crossing, and they're like we had before we stuck all the weights over in this first column. And then we have a now we can see some differences taking place in reversal. So we see the reversal degrees changing because we subtracted the crosshead weight out of there. So now we can see we went from this reversal to this reversal by manipulating the numbers in our geometry. There's some other things that we can do with these numbers in the geometry too. We can, by using these dynamic pressure reversals or these dynamic force reversals in here, we can actually line up crosshead knocks and other vibrations, and by using the component weights, and we can tell pretty close to where those components are actually, which one of those components is actually loose and causing the vibration that we see. But that's another course, so we'll get into that another day. Okay, so now we're looking at the your software setup, where you go to your rod, load, and reversal in your software options, like Brian showed you. And we chose the OEM as Ariel, and with the rod reversal requirements as Ariel, which says that we require 30 degrees of reversal at 25% opposing force. Now we're talking about opposing force there. We're talking about we have a total amount of force going on here. Okay, and we need to see at least 25% of this total force past the zero before they would call it a true reversal. Now there's several different things that you can do in there to change that. I mean, if you're just using a straight bushing, it might even be more than that. But they've got fluted bushings. They have all kinds of different things that you can put in those pin and bushings anymore that can help alleviate some of that non-reversal issues that you have. Okay, so now, as we showed before, so we have our piston and rod mass in here. We have our crosshead mass in here, because that's the way Ariel wants you to set it up. And then we go in here and we'll change it. We'll go Windrock total load instead of GE. And here we're using the maximum differential degree by degree pressure, and we're using the rod load, use the piston and rod mass. So they're saying that the rod is the most important thing. So that's the way we want to set it up. And we're going to use the rod reversal requirements for the API 618 instead of the engine manufacturer's specifications in there. These are pretty good. If you don't have an engine manufacturer's specification for rod load or reversal, then the Windrock and the API 618 is probably the way to go. And we can see here the API 618 says that the rod reversal is going to require 15 degrees at 3% opposing forces. Now we're talking about most of these big slow speed engines. They don't require as many degrees or as much opposing force to actually reverse that pin in the bushing. as the high speeds do. They've got a lot of time to do it too. Okay, then here we can see that this is actually the same data. We just changed the rod load calculation method to the Windrock total rod load and the API 618 on reversals. And we can see quite a bit of difference now. So we can see that the rod load calculations that we're getting and the reversal calculations that we're getting are quite a bit different from what we had under the aerial calculations. See, so we went from this to this on our reversal calculations. So as Brian was telling us, that we need to know what the manufacturer recommends for your equipment. That's some data that you're going to have to look up or try to locate somewhere. And like I said, if you're running aerials, the software, their sizing software has all that information in it for you. And some of the other ones, it might be a little difficult getting that information. But if you've got the old books on it, I've spent hours delving through the libraries at different locations to find the actual paperwork and the books that they got with the particular piece of equipment when it was set. Some of it's 40, 50 years old, but that data was still there. So had to dig through their libraries and find that information in order to set it up in the software correctly. Okay. Thank you for joining us today. And then here's Brian and I's contact information if you need to get a hold of us. And I'm sure Dylan's got some questions. So.
Yeah, there are a few other questions here. I think Brian's been answering some in the background.
Oh, thanks, Brian.
Yeah, I was wanting to know, Mike, about when you're trying to figure out inertia load, should you use the nut, the piston rod nut? Should you use the balancing weight? Should you use the pin? You know, your crosshead pin? I mean, what components in the throw should you use to try to figure your inertia?
Yes, all of the above, everything except for the connecting rod. Okay, then they have certain criteria and rules on that pin too. Okay, some of the old Worthington compressors, they had what they call a captured pin, where you actually had the end of your connecting rod had a clamp bolt on it that clamped down on the pin and would not allow it to move inside the connecting rod, and then the bushings were in the crosshead. Okay, then we have some that where the rod is the only bushing in it is in the connecting rod, and the pin is actually captured in the crosshead assembly, so it's nailed down in there. And then you have some where it's free floating, like the aerial, where it has bushings in both the crosshead assembly and bushings in the connecting rod. So the rule of thumb on that is if the pin is captured in the connecting rod, we do not use the pin weight.
Okay. If
it's captured in the crosshead and has a bushing in the connecting rod, then we use the entire pin weight. Okay, if it's a free floating one, then you have to consult the manufacturer or use half the pin weight. That's what the rule of thumb is. Where we have bushings in both the crosshead and the connecting rod, both.
All right.
And then everything else you would want to use, balance weights, which would be part of your crosshead assembly, jam nut, balance weights, all of that would be part of your crosshead setup and not your piston and rod. On the piston and rod weights, we're looking for the piston weight, we're looking for the nut that holds the piston on the rod and the rod weight is what we're actually looking for there.
All right. Okay, here's one that says that I understand that gas forces affect rod load, but do I need the weights to calculate pin bushing load?
Yeah, actually you do. You need those weights in there to calculate your pin load.
Okay.
And like I said, sometimes those weights are very hard to find. So if you don't have your weights in there and you get a rod load with reversal on your calculations there, if your rod load goes a little bit above or a little bit below your compression and tension limits in there, then you have to You have to kind of figure in your head, well, the inertia weight's going to subtract a little bit from that. And it's probably going to alter the reversals as well. But, you know, if you don't have the weights, you just have to get along without them. I mean, we've been doing that for years when we couldn't get them.
Yeah, if I don't have weights, I'll use it. I'm pretty close to reversal. I'll try to throw some weights in there. I'll make some up what I think might be pretty close.
Yeah.
Just to see how it affects it. Sometimes it helps it, sometimes it hurts it. Yeah.
Yeah, I've gone back through all my databases and stuff and found compressors that were similar, you know, to try to calculate the weights. You know, aerials, you can go, you know, total weight, crosshead and everything. You're looking at 230 pounds up to 300 pounds, something like that. But some of those old big HHEs and things like that, you may be looking at 1,500 pounds of slinging mass going on there. So, you know, you can probably guess pretty close within a couple of 100 pounds on one of those big ones, which will help you out.
Okay, so yeah, we can guess if we're close. I mean, if you win, you know, 50-50, you know, it's not really, I'm not too worried about it, but when we're close, it kind of.
Yeah, right.
Okay, here's another one. What valve failure on the head or crank affects reversal the most?
Yeah, probably if you have a discharge valve on the crank end, it's going to affect your reversal more than anything else.
Okay,
and why would that be? Is because you have less volume for your gas load to effectively dampen the inertia load on the crank end because it has less volume because of your rod. So that's the most dangerous one to unload at discharge pressure is your crank end.
Okay, and I guess that's why we unload the suction valve on the head end first.
That's exactly right. Yeah.
Okay.
Yeah, once you unload the head end, then if your next stage, you went to 50%, then you go to 100% and unloaded the crank end, then you still have your inertia in there that's going to reverse that pin and bushing.
Okay.
Got another one here, Mike. If you go back to the slide where you can choose your OEM rod load calculation and reversal. So we show two options. Windrock options, windrock calculations. What's the difference between those?
Well, one of them is you're not using the total rod load, which would mean that we're not actually using the inertia in there. So we can choose to use the gas load only, or we can choose to use the total rod load, which would include your inertia weights.
So what's the best one to use if our OEM is not listed in that list? What would be the best one to use?
Well, if you don't have all the weights, then it really wouldn't make any difference which one you push. If I didn't have the weights and didn't have any intention of putting any guesstimated weights in there, I would use just the Windrock gas load only.
Okay.
Does that make sense, Brian?
Yeah, and we had another one too. The question was, do different OEMs have different requirements for degrees of reversal?
Oh yes, and some of them won't even make a guess. They suggest this or they suggest that. They won't actually let you pin them down on an actual calculation requirement. So, yeah, all the different OEMs have different reversal requirements as well.
Yeah, if you go back to that slide where you have your reversal points on the actual graph. Yeah, right here. So I guess if you got 112 here and 135, if you add those two up, that doesn't calculate to 360 degrees.
Well, there's two different explanations for that. We don't get 360 out of this because we had this amount and this amount that were above the manufacturer's requirements for reversal. And also because of the fact that we don't have much piston motion at top dead center and bottom dead center. So we may have, some of those large compressors, we may have 4 or 5 degrees of crankshaft rotation where there's no piston movement at all. So that actually goes into that too, as well as what the manufacturers recommended.
All right, so the software doesn't start counting down how many degrees of tension until you satisfy.
Until you satisfy the 3 degrees or 3% differential pressure or whatnot.
And the last one here, I know we're getting kind of close, Dylan. Does the speed affect the rod reversal?
Oh, heck yeah. Oh, yeah.
It affects the inertia force.
Yeah, it affects the inertia force, and then in turn, the inertia force is going to affect the reversal. Not as much as you would think it would, but the speed will make a difference. As a matter of fact, a lot of times if we try to run some compressors at a low speed, say we have a compressor that's designed for 1200 RPM, and we try to run it at 600 RPM, you may go into a non-reversal in certain situations because you're not generating enough inertia in order to offset the gas loads. Or you're not generating enough inertia to actually reverse the pin if it's close. So, that's just something you have to go over with your manufacturer, do some testing and see what it is.
Awesome. I think we're at our time for today. We want to thank everybody for joining us today. I know it's tough to take an hour out of your day to join us for a webinar presentation. So hope everybody was able to learn something. I know I learned something from Mike and Brian every time I talk to them. So appreciate you two presenting today, and thanks everybody for joining. Be on the lookout for future webinars. I think we're trying to stick to bi-weekly now, so we'll have another one in a couple weeks on a new topic. Thanks everybody. Have a good day.
Thank you, Dylan.
Thank you, Dylan. Appreciate it, guy.
Thank you.